This is an energy balance problem. In this problem, we will calculate how much energy it takes to cool a can of beer from 35 degrees to 0 degrees. We are asked to list the assumptions. One of the assumptions that we will make is that beer has the same properties as that of water, irrespective of the temperatures that we are studying here. We need the system and we will write the flow diagram. So we can assume that the beer is coming in at 35 degrees and it's going through a unit, and then it comes out at 0 degrees. And obviously heat is given out by the system, so we know it already here. So now we can write the energy balance equations that we learned, which is the mass times the specific enthalpy of the inlet stream minus the mass times the specific enthalpy of the outlet stream minus the heat, and we're not going to consider any shaft work. So all of this, when you add up, they have to be equal to 0. So that's the energy balance equation. And the H in and the H out, you can get in from the steam tables or on the internet. And if you take a look on the internet, H in, it has a value of 146.64 kilojoules per kilogram. And the H out, it's going to be 0.06 kilojoules per kilogram. Okay, so we pretty much have got everything. So you just have to plug in the value of M, plug in the value of the specific enthalpy, and there we are. We can calculate the heat which is being released by cooling a can of beer. And we also were given that a can of beer, a beer has a volume of 33 centiliters, and this is where a number of you made mistakes. Centi, the prefix, is actually 10 to the power minus 2. Okay, so if you want to convert 33 centiliters, we need to convert it to kilograms. So how do you do that? So 33 centiliters, and centi, the prefix, is actually, we can say, I think that's a bit confusing. Let's say centi is equal to this 10 to the power minus 2, then we can cancel out the centis here. And a liter, 1 liter, what are we doing with this? Because we need a conversion between liter and mass, which is the density of water. The density of water is 1000 grams per liter, or 1000 kilograms per meter cube in SI units. So because we need mass in the numerator, so we're going to divide the volume by the density. So which is going to be 1000 grams per liter. So that's the density here. So then the liter cancels out, the centi cancels out. So we've got this term. If you multiply these three numbers, then you get 33 times 10 to the power minus 2 times 10 to the power 3 grams, or 0.33 kilograms, because we wanted the units in kilograms here. That's why we're getting it here in kilograms. So now we can plug the value of mass, which is 0.33 times 146.64 minus 0.06 kilojoules per kilogram, and then this is in kilograms. So when you multiply that, you get the kilojoules. It's 48.4 kilojoules per can, actually. That's per can of energy that is being lost, because Q is positive here. That means heat is given out by the system. So that's the Q for 1 can. But then the second problem was we have to calculate for the whole year for Estacao Barao, assuming that there are 200 people visiting every day, and each of them have 5 beers, and Estacao Barao is open 300 days. So we can calculate the number of beer drunk in 1 year, which is 30 multiplied by 10 to the power 4 beers. Yeah. So you know the energy that is released by one can, and you've got all these cans. So simply we need to multiply 48.4 kilojoules per can, and the cans they multiply out. And your answer is pretty much here, which is 30 times 10 to the power 4 times 48.4 times 10 to the power 3 joules. That's it. But then you have to convert this to the units kilowatt hour, and that's where again many of you had difficulties. So this is the unit of energy. You can't just simply multiply by time. It's not allowed, because you can multiply and divide by time, but you can't just only multiply by time, and that's what some of you have done. So if you multiply that, it's going to be 10 to the power 7. 4 times 3 is 10 to the power 7 joules. 48.4 times 30. 1452 times 10 to the power 7 joules. So that's the total energy that is being consumed by Estacao Barao in 1 year. But I want to convert this to kilowatt hours. So I know that 1 kilowatt hour is equal to 3.6 times 10 to the power 6 joules. So if I multiply, it's going to be 33.33 kilowatt hours. Yes, because watt is the unit of power. It already has joules per second in it. So you're multiplying it by hour, which has the unit of time. So they cancel out. That means you get the unit of energy, which is joules. Yeah, so this is where again what some of you did wrong here. So 1 kilowatt hour is actually, what is it? So 1 kilo is 1000 watt hours. So watt hours is 1000 joules per second times hour, and then 1 hour is 3600 seconds. So hour cancels, second cancels. 3.6 into 10 to the power 6 joules, or 3.6 megajoules. Yeah. So these are all the range of values that some of you have obtained. See, the first one is 4.03 times 10 to the power 10 kilowatt hour. That's 40 terawatt hours. That's nearly half an Estacao dam. Do you think Estacao Barao consumes half an Estacao dam in 1 year to cool a few thousand beers? This one, 4,000 kilowatt hours. That sounds reasonable, because my monthly consumption is around 100 kilowatt hours for one person living in a flat. So that could be reasonable. This one here, 1.98 10 to the power minus 3 is 1 kilowatt hour. It costs nearly, I think, 20 or 30 centavos. So it's absolutely free. 1.98 times 10 to the power minus 3. That seems wrong. You're paying 60 centavos or 1 real for this. Doesn't make sense. That sounds reasonable. This one is 10 times higher than the other ones. This is, you see, these are 0.11. So you can see a range of values that people have got, and actually it's approximately 4,000 kilowatt hours. That's what is the right answer. Okay, so really make sure that you get the order of magnitude right. Otherwise you can't make any estimation in doing any calculation really.